Welcome. So I'd like to present Mr. Hisham Brahim from IPRAP NCC, who's going to do the presentation about how internet works.
Thank you, Mohammed. Good morning, everyone, and thank you for coming. My name is Hisham Ibrahim, and as Mohammed mentioned, I work for an organization called RIPE NCC, and we'll be touching on that in a second. The talk actually gives a high-level understanding of the internet and the organizations that support it, and gives a quick overview of some of the technical aspects here. Now, my understanding is we do have people that do have a strong technical background. So if you feel that this is, something that you commonly know, let me know and we can move on to other bits. But for the rest of the attendees that do not, we'll be walking through them slowly and understanding each and every concept. Now, the slides start out with a very simple question, which is, who runs the internet? The internet now has become a very important and integral part of our life. Everybody uses the internet here, whether for work purposes, productive purposes, leisure, social. Everybody now uses the internet. And the question is, if it's become this important to us, has anybody actually stopped and thought who actually runs the internet? Does anybody have an answer for that?
I once read it online.
Sorry?
I once read it online. It's like a kind of three persons, they are in different continents, and they have the. It's not as simple as it sounds, but.
Yeah. Okay.
A few researchers about it, but.
Fair enough. Key people and organizations that have continental perspectives. Okay, that's a good answer. Anybody else? Yeah, please.
All goes out with the root DNS, which basically saves all the two-way DNS service, and those 6 root DNS are owned by 6 different companies.
Okay, DNS and domain name services. We're going to talk about that as well. Yeah, anybody else has an answer? Yeah? Governments?
No, actually, they try to segregate the governments from this.
Okay, fair enough.
They try.
Okay, fair enough. Well, so the answer is, and the simple and short answer to that question in general is, who actually runs the internet? No one in particular runs the internet. There isn't one particular organization or person that you go to and ask permission to become part of this internet or get their stamp to validate your, software or website or application that you're running out, right? There isn't one particular bit that actually controls how all of the internet works. But it's not as simple as that, right? Because something as big as the internet, it does need coordination. It does need some kind of engagement with people on different continents, on different places, with different backgrounds that can actually do this. And for us to actually properly define who actually runs the internet, we actually need to look a bit closer on what the internet is. Now, we usually, when we draw the internet in a diagram or something, we actually try to show it up as a cloud, right? This cloud that we call the internet, and people connect to it. But the internet isn't this just one big homogeneous cloud. In fact, it's a bunch of clouds. It's a bunch of networks. These networks could be academic networks, like here at the AUB. You guys run a network here. Could be governmental network, the ministries, the regulators, the other public sector offices. It could be banks. It could be ISPs, of course, the Ujiro, the Touches, the IDMs of the world. It could be content providers, the Googles, the Facebooks, and so on and so forth. And these networks, they have to all interconnect, because if one of these clouds isn't connected to at least one other connected cloud, then it's not really part of the internet. It would be what we kind of call like a small closed intranet or small closed network that isn't really part of the internet. For you to be able to be part of the internet, you have to be connected to another network that connects you to the rest of the world. Now, today, the internet has more than 55,000 networks all over the world. that interconnects, not necessarily directly to each other. It's not like each and every network has 55,000 connections to the rest of the world, but they have to at least have a single connection to one that is connected to the rest of them. Okay, makes sense? And the question now about, who runs the internet, going back to that question, is how do they coordinate amongst themselves? If there are 55,000 different networks around the world and there is a new network popping up in China, does it meet up with the 55,000 other ones? Does it coordinate with them in any particular way? How do they know how to communicate together? How do they know how to exchange the information back and forth? Right? And for that, there has to be these common rules of engagement. This is how we all agree we will be sending and receiving information back and forth. Right? Certain handshakes, certain protocols that are put in place that allow these networks to pop up all over the world and be able to instantaneously connect with everybody else and talk with everybody else. Right? Now, there are a number of standardizing bodies that look over this. You probably have heard of some of them. There are others that look at other aspects of being connected, but the ones that are directly connected to the internet and its technology, first one is called the IETF, the Internet Engineering Task Force. Now, these are the guys that sit down together and come up with the protocols that are put online. So when we're talking about stuff that relates to routing, for example, BGP or OSPF and other routing protocols, these are the ones that work on enhancing that and making it better. When we talk about DNS systems, for example, and how technically the bits go back and forth, these are the guys that will be talking about it. When they talk about stuff like smart object networking, which the marketing name for it is now Internet of Things, these are the guys that sit down together and actually say, this is how we think the handshakes should look. This is the acknowledgement message. This is how we send this. We wait this amount of time before resending the message again. These are the ones that actually sit down and put those bits together. Another group that standardizes bits that go to the internet is, related to the internet, is the World Wide Web Consortium, W3C. These are the ones that actually put the standards for how you write websites and web applications, the get, push, and other commands that people now take and use when they're building their websites. These are the ones, like I said, that are directly connected to the internet. There are other standardizing organizations that look at aspects that indirectly work with the internet. For example, at GSMA, which is a consortium of the mobile operators, they have something called the 3GPP. These are the ones that gave us 3G mobile, 4G mobile, and now we're discussing 5G mobile and beyond. They're talking about aspects related to Internet of Things and other bits. So it's indirectly connected to the internet. It doesn't impact the plumbing of the internet, the routing, the switching, and all the other bits, but it will impact and shape how the internet reaches everybody through their mobile devices and other equipment, how the internet will look moving forward. Now, the reason why I'm putting these things up is these are open fora. They have mailing lists that people can subscribe to and follow and actually participate in how to shape the technology moving forward. Because we've always been given technology in our part of the world, right? We're kind of more on the consumer side than we are on the innovative side. However, there is no closed group of people that actually sit down and discuss and come out and say, this is how the internet is going to look for the next 5 years. Actually, through these open meetings, they actually sit down and discuss, and anybody with a good idea comes up with it and discusses it, and the basis of running this is rough consensus. Not everybody has to completely agree with this, but if there's a general acceptance of this is the way forward, then that's actually what they adopt, and all the vendors participate there, all the content providers. So you find the Apples of the world, you find the Facebooks, the Googles of the world, they participate in there because they also want to keep up with the latest technologies and the latest fixes and the latest bugs that people have identified to stay ahead of the game. Make sense? Now, the reason why these... Yeah, please.
The question concerning the W3C.
Yes.
I knew that they set the standard for the HTML code and for Web 2.0.
Yeah.
Currently, it is not enforced. I mean, none of these are enforced. Anyone can write their own code.
Yeah.
What's the purpose of having these standards?
Which is exactly the point that I'm going to with this now. I mean, there are two kinds of ways of doing this, right? There's the standards, the common rules of engagement that everybody agrees on, right? And there is also the proprietary way of doing so. You may disagree with what is considered to be a standard, and you come up with your own thing, right? However, the problem with coming up with something proprietary is not everybody complies with the same way of thought, and interoperability becomes an issue. Right? When you now buy a Wi-Fi capable device, Wi-Fi is a standard. It's not standardized by these guys, it's standardized by IEEE. It's IEEE 802.11, right? When you buy a Wi-Fi compatible device, right, it says Wi-Fi on it. If you buy it in the US and you come and turn it on here in Lebanon, you know for a fact it will work because the standard is the same. Everybody agreed on how to do this together. However, if you're using a proprietary technology that is still capable of sending and receiving information over probably the same bandwidth frequency. However, it doesn't really use the same handshakes back and forth. Then you need something to translate that back and forth. You need a gateway to actually be able to translate between those two protocols. And that adds more and more complexity to the system, right? So the reason why these open standards exist is for this point, to have permissionless innovation. Now when anybody has a good idea, has an app, has a way of doing things, he can just deploy it and put it online and it becomes public. People can use this, people can take it off right away. You don't need to go to certify your app or your website or your network at an organization and wait for them to approve your technology and say, okay, this is something that, you know, half of the world can deal with, but the other half, because they're using another kind of technology, they're not using. And that's actually why the internet has actually grown and flourished the way it has. Anybody with a smart idea has been able to put it online. The example I've been giving for the past couple of days when I've been talking about this is there's the movie about Facebook, social networking, right? Have you guys seen it? The guy that's playing Mark Zuckerberg's character, when he came up with the concept of Facebook, he just put it on a server in his bedroom at Harvard University, and it just became a thing. And people were using it until he actually crashed Harvard University's network in the movie. And that's exactly, he didn't have to ask anybody's permission because he complied with those common rules of engagement of how things communicate online, and he put it out there and it started working, right? And that's the thing. I mean, and even with Facebook, continuing with the example I gave, I mean, before Facebook, there were predecessors before it. There was something called High Five, and there was something called MySpace and other social networking bits. But then, you know, what prevailed is what people actually started liking to use more. So people started leaving those places and going to Facebook, and maybe leaving Facebook at one time and going to other stuff. And that is how the internet continues to grow and flourish. Because if it were just one organization that would actually say, this is the way we think social networking will work for the next 5 years, it wouldn't be as successful as it is today, right?
That's the case. I mean, take an example, Google.
Please.
Google, they release sometimes protocols that they develop, and
Yeah.
it's not part of the IETF. They develop the protocol like equipment.
So what they do is, yes, so at the IETF, let's talk about the IETF for a second. When people participate at the IETF, they do not participate as organizations. I mean, you could be working for Google, and people would know that you work for Google, but it's not when you go to the mic or you propose a protocol or a new way of doing things. You don't go, this is how we think things should be at Google, and we think the rest of the world should comply with this. They actually go...
But again, I mean, Google owns probably 70 or 80% of the traffic on the internet.
Yeah, but
They can take
so let me tell you how they do this. Like I said, they do participate at the IETF, and if they see something that they want to fix or standardize, for example, Google had 2 very smart engineers that were working on fixing IPv6 at Google, and we're going to talk about IPv6 in a second now, right? And they actually identified a lot of bugs that they saw in production, because Google was one of the first content providers to move to do IPv6, and they have an IPv6 only network. right? So they actually managed to identify a lot of bugs that they saw with IPv6. Now, they figured out ways around them and they figured out ways to fix them on the network, but they wanted to standardize that so that other people, when they actually start working with IPv6 and IPv6 only networks, they can actually, you know, not have to go through all the hassle that they went through. So they would go to the IETF meeting as their person, not as Google saying, this is what we think should happen because we're Google. They would go as their person and say, we deploy a large network, you know, and we've been facing these issues, and we propose something. So the way the IETF works is you propose, they do like an RFC, a request for comments on papers and protocols that were there already. So they would propose an RFC to fix something, a bug that is there in one of the protocols that already exists. And again, if there's rough consensus from the room that this makes sense, and if they make the case well enough, then it can actually become a protocol or fix a protocol or features in some of the protocols. We've seen this already a lot with IPv6, where people come up with ideas and say, we would like to change this because we're used to this, or we haven't seen this work, or so on and so forth. We've seen this even with other protocols, not just with IPv6. For example, let's say BGP. BGP is something that every single network uses to communicate with other networks, right? Today at the IETF level, operators are talking about securing BGP, doing something called BGP-SEC. They're still figuring out how they can actually do this and implement this, but once they do that, then they will be able to secure BGP and the connections, the communications back and forth to these different entities. And we can touch on that when we get to that bit at the end there. But did that answer the question? Mm-hmm.
Now part of Chrome.
Yeah.
But it's not a standard.
Then it would be a proprietary. Yeah. It would be a proprietary system. It wouldn't be an open standard, but so there are a lot of proprietary systems. So let's take, for example, not just Google as an example. Let's take Cisco, for example, as one of the biggest vendors for networking, right? They do comply with a lot of the open standard bits, but they also have their own proprietary protocols actually to figure out stuff on Cisco. Now, the problem with that is if you run a multi-vendor network, then you cannot use those proprietary bits. And that's a risk that Cisco takes, because on one hand, they would love to lock you down to only one vendor, which is their stuff, so that you buy every single bit of your stuff, so that you can use the cool proprietary features that they've developed. But on the other hand, if you use a multi-vendor network, which most people actually do, then you cannot use those features. And when they come and say, oh, but we're giving you this and it's awesome, you can say, but I cannot run this across my network. So it's a compromise between, yes, a lot of people develop proprietary bits and they see a competitive advantage in doing so, but also not everybody is locked now to one vendor. Right? If, like you said, if using Chrome is forcing people to use a certain thing, there are other browsers out there that don't necessarily, aren't necessarily Google and not Google related, right? And they need to take into consideration that when somebody is developing stuff for other applications. I know for a fact I've faced this before, where a certain app was designed only to work with Windows Explorer, and I use a Mac. I couldn't access the application, and it was actually a governmental application for me to apply for residency in a country, and I couldn't use it because I had a Mac. So again, being locked to one vendor isn't necessarily the best way of doing this. Anyway, moving forward. So going back to the question again and looking at the internet through a different perspective, right? The internet now has roughly 3 billion users online. Now, the entire planet has roughly 6 billion people on it, so more than half of the world's population is now connected, right? And for them to be able to send and receive information, because the internet, in its simplest form, the way it works is, it works like the postal system. Back in the day, when people were still sending out posts, what you would do is you would get an envelope, and you would write your address as the sender, you would write the destination address, where you want to send it to, and you would put whatever your postcard or your letter inside that, right? Today, the internet works with the basic same function, right? The packet is the envelope. and you put your sender address and destination address in there to identify who you are and who you're sending it to. That way it finds its way through the internet to the place you're going to, and then it finds its way back to you with the information that you've sent. And the postcard or the letter, that would be the payload that you're sending out in the information. So there is need to identify sender and receiver addresses, identification that allows you to know where you're going to on the internet and how people can reach you back. And in the internet world, we call these internet number resources. Right? That's just a way of calling IP addresses, whether IPv4 or IPv6. That's a way of coming up with identifiers for networks, something called autonomous system numbers. I'm going to be touching on those really quickly now. So two devices, when they communicate using binary, right? Zeros and ones, ons and off switch, that actually constitute for the name of the device and its address. Now we as human beings, because we do not care to remember these long binary codes, so we've shortened them down into decimal, 10 fingers, 10 a decimal code, and this is how an IP looks like. I'm sure you've all seen this and dealt with this before. Now this is what is called an IPv4 address, right? There are roughly 4.2 billion IPv4 addresses. Not all of them are in use. For different reasons that were standardized through these RFCs, through the IETF. But worldwide, there are only 4.2 unique different IPv4 addresses. We just said there are 3 billion internet users, right? So if we're just talking about users, then we can actually see that, you know, they're almost run out. Now, as an individual user, you don't necessarily only have one device that connects to the internet, right? You probably have a laptop, you have your phone, you have an Xbox or a PlayStation back home, you have, you know, a navigation system on your car. So you actually end up consuming a lot more IP addresses than just one as a human being, right? That doesn't even take into account, you know, machine to machine, the DNS system, and other bits as well. So it was very clear early on, and even though it's still the most commonly used IP identifier, but it was early on figured out that this will not scale. As the internet starts growing and growing, it will not scale. And these 32 bits that constitute for the IPv4 addresses are not enough. The reason why they also have to be unique, so we only said you have to use you only have 4.2 billion unique ones, right? Why can't you recycle and reuse those IP addresses? Because if there are two IP addresses that are identical, two destination addresses that are similar, your device will not know which one it's talking to, right? So there has to be unique public IP addresses that people can actually be able to reach you over, right? Make sense? Now, when we were talking about who runs the internet, this guy was the closest thing the internet actually had to somebody running the internet. His name was Jean Pastel. He was an academic, and he was the man responsible for the distribution of these IP addresses. He would literally walk around with a notebook, and when somebody would say, we want to be part of this experiment that you're calling the internet now, and we require IP addresses, he would say, okay, I will provide you with, at the time they would call it a class A, which is now what we call a /8, which is roughly 16 million IP addresses. I will provide you with one of those so that you can run your tests at your university, and that's why a lot of universities now have a lot of what we call legacy space from that time. Now, as the internet started growing and it started spamming into Europe and going into Asia Pacific, and this guy was an academic sitting in the US, they figured out quickly also that it will not scale to have him running this operation. And that is where they came up with an idea. They said, okay, let's gather all the unallocated IPv4 addresses that nobody's using it and put it in a main reservoir called the IANA, right? And the IANA would then distribute to, as you mentioned earlier about the organizations that look after continents, it would actually distribute them to 5 different organizations, each one looking at roughly a continental size service region, right? So you have AFRINEC for Africa, you have APNIC for the Asia Pacific, you have AREN for North America, you have LACNIC for Latin America and Caribbean, and you have RIPE-NCC, the organization that I work for, that overlooks Europe, Middle East, and Central Asia, right? And then these organizations would thus give the resources to its members from the ISBs or from NSIDE. So the AUB here is a member of the RIPE-NCC. They get the resources directly from us. But for example, we were at Balamand yesterday, Balamand University. They get their resources from an ISP, IDM, that gets its resources from the RIPE-NCC, right? And then when the RIPE-NCC feels it reaches a critical number of IP addresses that they require more, then they go up to the IANA and request a big continuous block of that class 8, the /8, the 16 million IP addresses. And now, this is a graph that shows the service regions. Like I said, roughly each one of these organizations overlooks a continental size service region. Now, yeah, somebody's taking a picture. Now, what happened is, and the reason why I'm mentioning this is, you probably heard of something called global IPv4 depletion. And what that actually means is that there are no, well, what happened in 2011, February 2011, is that IANA, the main reservoir, ran out of those big continuous blocks that we were talking about that they would distribute to these 5 RIRs, regional internet registries, that I just mentioned. So at that point, they said, we have no more to give back to you. Maybe we have bits and pieces that we can distribute later to you guys, but there isn't this one big continuous block. And the reason why they would distribute these one big continuous blocks, to help with aggregation, to help aggregate the advertisements of IP addresses per region. That way it would have helped the routing table not explode the way it did. So the IANA ran out of IP addresses 2011, and it was left to each one of these 5 RIRs to work with their communities, to talk with their members and people that have a stake in the internet, in seeing how do they want to use these resources moving forward. Because the way that the internet worked with this model was, if you can justify getting a large amount of IP addresses, you would get that. So if you said, for example, I am a mobile operator and I have 50 million customers, you can actually get 50 million IP addresses. So, but the problem was, now that IPv4 became more and more scarce, if an organization or an operator like that came out tomorrow and said, I want 50 million IP addresses, and then another organization came out and it took them, and then another organization came out and said, well, I only need 50, you face the risk of the RIR saying, oh, well, I just had 50 million yesterday, I gave them out, and now I don't have any, right? So what happened in each and every one of these communities is, their communities put safeguards to help with the growth of the internet, to make sure that everybody still has at least a small amount of IP addresses that they can actually still run and maintain their networks with. And as predicted, of course, they started running out. So the first one to run out was Asia Pacific. They have large communities there, China, India. They ran out really quickly. Then after that, RIPE-NCC, Europe consumed a lot of IP addresses. LACNIC, ARIN, the only one with still more than a class A/8, 16 million IP addresses, is Afrinet. And that's because the consumption rates in Africa is a lot slower than it is anywhere else in the world, right? And what that means is that now that triggered the policies that I was telling you about, that the community came up with which says that there's only a limited amount of IP addresses a member will get, whether they have five users or they have 50 million users. It doesn't make a difference. Moving forwards, yeah, you can only get 1,000 IP addresses. That is it. So if a new ISP popped up here in Lebanon, they can only get 1,000 IP addresses. If a small office starts out here, they can only, and become a member of the NCC, they can only get 1,000 IP addresses. And that is what is meant with global depletion, because now, even if it's not a new ISP, even if it's, you know, Ujero or IDM that want to roll out a new service or want to do broadband in the country, or want to do something regional where interconnecting all of the Levant together, using IPv4, they can only get at one time 1,000 IP addresses after depletion, after this happened, right? So this was the RIPE NCC region, the region that we're talking about here. This happened in 2012. So starting end of 2012, September 2012 to be exact, there were no more blocks to give out, right? Now, at the IETF level, they saw this coming a long time ago, and they came out with different things. There's NAT, for those of you that know what NAT is, and it was, at the time, it was, so NAT is basically providing virtual IP addresses to a network and having them translated as it leaves the network. Because online, you have to use public and real IP addresses, the ones that we were talking about distribution. However, what NAT would allow is, instead of giving this room here 30 public IP addresses, it will give 30 virtual IP addresses that mean nothing on the real internet. But then they have to go through a box, and that box would then remove the virtual IP address, put a public IP address at it, send it out to the destination it's going to. When it comes back, it removes that public IP address, remembers who was sending this packet out, put the virtual IP address back, and gives it back to you. Now that allowed the existence of IPv4 to be prolonged a bit, right? Instead of it running out in the late 90s, early 2000s, it allowed it to continue to be around. And NAT is a commonly used way of doing this. However, NAT was intended, and this is in the RFC, to be only a temporary solution, wasn't intended to be the way that to build the internet and moving forward, even though a lot of operators became more and more comfortable using NAT. However, now, because of this, the NAT numbers, I mean, the roughly acceptable number is NATing 16 people behind a certain IP address. That's roughly the acceptable number due to number of ports and other bits. Yeah, please.
I'm an organization. I would ask you, what's the disadvantage of using NAT? I mean, you don't need to have all your devices visible on the internet.
Yeah.
So most of the appliances are now cloud-based, so you can access your appliance at home without having a device.
Yeah. So the issue behind NAT is that the more people that actually start sharing an IP address. So like I said, all the way up to 16 users, if you do the math in terms of ports and port sharing, right? All the way up to 16 users is fine. Once you go beyond 16 users on a single IP, sharing a single IP, you start compromising by the number of ports you can actually provide them with. Now, a lot of the applications that run now, in order to provide you with services faster, something like iTunes, something like Google Maps, it doesn't just start one session with you. It starts multiple sessions over multiple ports. Now, when you reduce the number of ports because you're adding more and more people behind an IP address, that means the service becomes slower and maybe even doesn't really show up the way it should. Right? It wouldn't function that way. But there's also other issues as well. We've been seeing coming out of Europe now that Europol, which is the conglomeration of the European police, are saying now when it comes to cyber police attack, cyber crime attacks, right? When we go to an ISP and it gives us more than 50 users behind an IP address, we have no way of actually going through the 50 people and figuring out who was the malicious person. And the thing is with NAT, because we've become so good at using NAT and we're becoming using double layers and triple layers of NAT, and we've been NATing, I've heard from operators, thousands behind a single IP. Not in Lebanon here, it's not that bad yet, but in other countries it is. It becomes more and more of an issue. And again, even the ones that invented NAT said this is a temporary solution. It was never meant to be the way forward continuing with the internet. However, the way forward, which they identified, which was IPv6, right? So in IPv6, first thing they did was, okay, IPv4 is 32 bits. Let us let us quadruple that. We will do 128 bits, right? Which allowed for a lot of new IP addresses to be introduced there. And actually, you may notice that the IPs are written a bit differently. They use columns here instead of dots. They use hexa, so from 0 to 9, and then A, B, C, D, E, F, which represents 10, 9, 11, 12, 13, 15. And yeah, this is how it would actually look like as an IP. Now, the significant difference is the fact that, and this was published by the IETF in 1998. And again, there was more than one competing idea of how they can do IPv6, but then rough consensus ended up going with this one. And that's how the process actually works. There are other ways of doing identification and networking. There's a whole bunch of them. Now there is something called DOA and DONA being proposed of ways to identify users instead of using IP addresses, for example. But still, till today, the underlying technology that everybody agrees on, if you're being connected to the internet, that means IP, and that means either IPv4 or IPv6. But the significant difference is that with IPv6, now you have 340 trillion IP addresses. It's a huge difference between what you used to have before with 4.2 billion. And they did this in mind in the late 90s, thinking already of how the internet will actually grow and boom into having stuff like Internet of Things and devices connected to each other and talking to each other. At the time, there wasn't that much consumption. They didn't really have watches that spoke to your phone, that spoke to a base station, that spoke to your car, but they predicted at one point this will happen, and to foster the growth of that internet, they said, okay, we need a lot of these identifiers. And that's what they gave us with IPv6. Like I said, IoT cannot happen without IPv6. Even before IoT, because IoT is built on connectivity, right? Even those, I mentioned 3GPP earlier, the ones that standardize 3G and 4G and beyond, and now talking about 5G. When they came up with the 3G technology, they said, we cannot use IPv4 for this anymore because we consider now IPv4 to be a dying legacy technology. And they built it with IPv6 in mind. So now all the mobile operators, anybody that has 3G capable networking boxes, they can do IPv6 because it is in the standard and it is in that was released and came out for 3GPP.
They still do nothing.
I'm sorry?
They still do nothing.
They still do NAT. They can do NAT. Okay, so in real life experience, we have seen this before with several operators that do NATs. However, it gets, because 3G and 4G and beyond, especially LTE, is a very IP-hungry technology, right? The thing is, going a step back, so the way they used to design telephony, right, was they used to have a cutoff number, right? They would say, for example, we have 100 lines, but we will oversubscribe and sell 1,000 lines because we probably predict that not everybody will be picking up the phone at the same time. Those 1,000 people will not pick it up at the same time. And only 100 of them will probably be using that at the time. And that is why if you're like in a concert or in a party or something like that with a huge amount of people and you try to call for your driver or your parents or something like that, you end up with something called network busy, right? Because they've oversubscribed the amount of people there, right? They try to apply the same concept with networking. And it kind of worked at the beginning because, yes, not everybody was using their IP at the same time, and that's why you can allow and do sharing, right? But now, with all these always-on apps that you have on your phone, for example, your WhatsApp is always constantly asking, is there a new message for me? Facebook is always looking for updates. Your phone is constantly communicating with more than one bit on the internet and maybe more than one device in your network. It's always asking that. So it would never release that IP address, right? So more and more so if you give it that IP, it will never give it back. And as you oversubscribe people, then you have to end up doing NAT and double NAT and more and more. And especially that these technologies, like I said, are very IP hungry, never releasing the IP. And what a lot of operators have actually seen, especially when it comes to the bigger customer-based ones, the ones that have like 50 million customers, like T-Mobile in the US, for example, NAT doesn't work because it doesn't scale. And they actually went down that road, and then they went we need to do IPv6 only, not even dual stack, because they couldn't get 50 million IPv4 real addresses to give it to their customers. And that didn't work for them. Some people may say, yeah, this is only in the US and we don't see this here. We are seeing this in operators in the Middle East here now, especially, like I said, in countries that have bigger customer bases. Sometimes in smaller countries that have smaller customer bases, it takes a while to reach there, but operators around the world are now seeing this and actually facing the fact that NAT isn't the best way to do this for them.
What's the percentage of IPv6 over IPv4?
In real life use?
Yes.
Okay, so next slide. Google shows statistics and saying, so this is the amount of users that reach Google over IPv6. And Google is saying, well, this is from February, but now around 16% of all of Google's users worldwide are reaching it using native IPv6 connectivity.
That's not a big number.
That is not a big number. Okay, so but look at it this way. Remember the key numbers that I mentioned. 2011, IPv4 ran out at the IANA level. Look at 2011. Look at how much IPv6 there was globally, right? There wasn't that much, right? NCC ran out 2012. And now we're talking 2005, so 2017. So in 5 years' time, that number went up from 0.01 to 16%. Right? And these were the ones that we're actually still figuring out, will it work, and the workarounds, and what we need to fix, and the bugs, and identifying them at the IETF and coming back. Moving forward, this exponential curve is expected to go up a lot more, right? And yes, while, like I said, IPv4 is still the most commonly used IP address scheme out there, however, IPv6 is picking up faster and faster. And like I said, now all it takes is a big operator, let's say like T-Mobile in the US, that decided to do IPv6 only for all customers. 50 million users turned on when they do that, right? Like I said, Orange Poland did the same thing. Again, a couple million users all of a sudden. The operator here in the Middle East, once they do that, actually we have a couple of them, not just one. One of them is doing IPv6 only, but a lot of them are now enabling IPv6 in countries like UAE, Saudi, Yemen, Iran. A lot of them are now doing IPv6 because they went through the different processes of even acquiring and buying IP addresses off of the parallel markets. And then they figured out that IPv6 is the way to go about this. Right? Now here in Lebanon, a lot of the operators are actually asking for this. IDM, Siberia, Alpha, and others are actually ready with a lot of the stuff. The thing is, their upstream provider, Ojero, hasn't really moved to IPv6 yet. However, Ojero is actually in the process of moving and doing that. And once that happens, we do expect the numbers from Lebanon here to grow up. Up and up. I know for a fact that the AUB here, you guys have a tunnel for IPv6. Now, an interesting thing that just happened a couple days ago, Sixes, which is one of the most famous tunnels out there, is saying that they're going to start shutting down their service by the end of the year because they're saying there's no need to do tunneling anymore because people have native. I don't think it's that clear, but if you can see in 2010, there's a small bluish line that is above the green one. I don't know if it's apparent or not. So blue was actually the tunneled services. And in 2011, there was more tunneled IPv6 than was native. Now you can't even see the blue curve anymore. And that's why the tunnel brokers are turning it off. Okay? Make sense? Yeah, please.
I don't understand if it's meant by tunnel.
Oh, sorry?
You said tunnel.
Tunnel, yes. Yeah, sorry. So tunneling means, what tunneling means is if you are on an IPv4 only network, but you have IPv6 capable device, for example, and you want to reach the IPv6 capable network and internet. And by the way, IPv6 capable internet constitutes for Google, YouTube, Facebook, Akamai, Cloudflare, all the major content providers since 2012 have actually turned on IPv6 and left it on. So if you want to do IPv6 on an IPv4 only network, what you do is you create a tunnel, right, that allows you to pretty much encapsulate your IPv6 packets inside an IPv4 packets, right? That way, as far as the guy running the IPv4 only network is concerned, when he looks at the packets going back and forth on his network, he only sees IPv4 packets going back and forth. But inside them, once they reach their destination, they actually are opened up, they get collected back into an IPv6 packet, and they get processed as an IPv6 packet. So it's just a way for you to go through the operator that doesn't allow you to do this. In this case here in Lebanon, that would be Ojero, right? Does that make sense?
When you say it's native, that means you don't need tunneling.
You don't need tunneling, yes, because now you have a direct connection over IPv6, right? Where you can just send it just the way you're doing it with IPv4, right? Now, to address something that was also mentioned again, do I have to have a routable IPv6 address where people can reach me directly? The way the internet was built was, yes, you get that peer-to-peer one-on-one connectivity, but however, you don't have to have that. You can advertise some of your IPv6 space and keep some of it unadvertised. You can still have, and there's a whole bunch, if you look at the IPv6 addresses and the way that it's configured, there's a whole bunch of them that are only locally acceptable identifiers that don't go beyond your network. So you still have ways of actually doing that, not necessarily putting you at risk of saying, yeah, anybody can directly target my device with a publicly identifiable thing. We kind of got that notion of security using NAT, even though that's not what NAT is and that's not what NAT provides you with. But you can still do something similar with it with IPv6, just to address that point. Anyways, is there any other questions on this? Okay, moving along. Another one of those internet number resources that we were talking about is something called an ASN, an autonomous system number. So an autonomous system is a network. So the AUB here is a network that has its own routing protocols, that has its own resources. We said it has IPv4 and it has other bits. So they get an autonomous system number that says this cloud is the AUB. If they don't have that, then who's the upstream here? Is it Ojero? Is it IDM? Yeah, because you have the ASN. But for example, if you only had one, let's say, which was Ojero, for example, then you would be seen as part of the Ojero network. You wouldn't have your own online identity, which is, this is our campus and this is how we do this. Now, the bit about having multiple connectivity is because when you get that ASN, you are now in control of your routing. You can now say, I want to send these packets to this upstream and I want to send these ones to there. And you can actually do that, and it's actually used a little bit more commercial as well, because especially for international connectivity, some of the providers may give you better deals on sending traffic to the US, and other them giving you better deals on sending them, let's say, to the Asia Pacific. So that way you look at your traffic and say, okay, I want to send my Asia Pacific traffic on the cheaper one, and then my US traffic on the one that gives me cheaper to the US. Right? You are more controlled to do so, and that's what this kind of allows you to do.
Does that define net neutrality? Since you're basically, it's prejudice, basically some data and some else. Isn't that against net neutrality concept?
It's not against net neutrality. So what net neutrality is, for those that don't know it, is it actually says that you should treat the traffic on your network equally. For example, if I am starting my own video platform, for example, on the network here, my package should be delivered at the same rate and speed as YouTube's, right? YouTube should not have an advantage because it's paying more money to my operator. Then they get a better quality of service and they get better, they get less latency than I do. Because that would create a barrier to entry, which wouldn't allow me to be able to compete and become the next YouTube. It will always keep the big ones on top, and the smaller entrepreneurs that are trying to come up with their ideas, they cannot do this, right? So that's what net neutrality is. But what this is actually being smart about how you spend your money, right? If you, like I said, if you get only from one provider, that gives you really good rates into the US because they have a direct cable into the US, but then they bounce your traffic all over the world and it costs you a lot more to go anywhere else other than the US, then now you have the power to say, okay, my US traffic goes there, it's fine, it's cheaper, and it gets there in better latency, but I still have a lot of people that want to view my content in India. And maybe somebody else will give me a direct connection into India with cheaper prices. And that way you're being smart about how you spend your money and how the user experience of how they see your content. Because if you go to the US and then India, it gives you a lot more delay than you go directly into India, right? Because, and I've said this a couple times this week, one of the basic physics concepts that we've studied is speed equals distance over time, right? Now, if the speed is constant because we're using the speed of light, because we're using fiber, right? So we're sending laser out there isn't anything faster than the speed of light, and you can't really alter it. So if the speed is constant, the further the distance is, the further time is. Right? And the shorter the distance is, the less the time it takes to reach there. So if you're sending your package to the US and then to India, it will take you a lot more delays and time than it is to send it to India right away. And that's a concept that the content providers, the CDNs of the world, content delivery networks, figured out a long time ago. And that is why they want to be as close to you as possible. Instead of saying, okay, we have our Google servers in the US, and anybody that wants to come fetch it from the US, they say, we want to have a cluster here in Lebanon, and we want to have a cluster in Jordan, and we want to have a cluster in Palestine. That way, traffic doesn't have to actually even leave the country, right? Facebook is doing the same. Akamai is doing the same, the one that gives you the Windows and Apple updates. They want to be as close to you as possible because they want to enhance your user experience. In shaving off even milliseconds of delay. Make sense? Yeah. Okay, so moving forward, we as human beings, we don't necessarily remember numbers, large numbers in binary or even in decimal. I mean, we all use Google and Facebook. We probably don't remember what the IP address is, even if you looked it up before. You wouldn't remember the IP address of the university network here, website I mean. Because we as human beings, we're more geared towards remembering names. My name is Hisham, you probably would remember that. You wouldn't remember my name if I said my name was 100111000. You would never remember that, right? And that is where there had to be a way that took and translated our way of thought into the way that these machines talk and communicate together. And that is what is the naming system. So basically what the naming system is, when you type in a URL, for example, if you're going to, let's say, the website here of the university, right? You remember aub.edu.lb. That's easy for us to remember, right? Even if it would be longer than what the IP address is, but it makes sense for you in your mind. And if you look at the anatomy of what a domain is, so you basically have here the top level, right? Top level could be one of two things. It could be the country code top level identifier, in this case .lb, that identifies the country, right? It could be .br for Brazil, .za for South Africa, .fr for France. It identifies the country that this URL has some relevance for. Or it could be a generic top-level domain, a GTLD, like .com or .info. And nowadays, they're coming up with new GTLDs as well. They were locked for a long time. Now they've opened it up. So now there are people purchasing .car or .shop or .museum or .green. And it's actually now coming up with more and more issues because, for example, Amazon wanted to buy, the shipping delivery company, they wanted to buy .amazon. But then the Amazonians, the people that actually lived in the Amazon, came up and said, wait a second, that's us. This is our national heritage. Well, how are you guys going to sell that out? I mean, who would have the right to buy, for example, .apple? Is it Apple, or is it the guy that sells fruit on the corner of your streets, right? Because he sells apples as well. I mean, and all these disputes and all these discussions have recently come up when they started doing this, because, like I said, for a long time it was closed on the ones that you would normally see and recognize, .info, .com, .net, .org, and so on and so forth. But now opening this up, there's debates about this. And we're going to see where these debates are discussed in a second now. Then after that, you go to the second level, third level, the host, what kind of service you're running, whether it's a web service or whether it's a mail service, webmail or something else, and what kind of protocol is being used. And again, the protocol stuff that would be identified in the standardizing organizations that we were talking about, the W3C and others, right? When you type in this URL, what you do not actually type in is, because you do www.aub.edu.lb, you don't end it with a dot. But actually what your browser does, without you even knowing, is it adds a second dot there at the end, right? And that dot represents the root. So when we were talking about the DNS system earlier, basically what happens is, if I'm a device that is communicating for the first time, trying to find for the first time ever on the network how to reach aub.edu.lb, right? If somebody before me did it, then it's probably cached and I'll get the answer right away from my DNS. But if it's for the first time ever that it's being asked that question, I want to look for it. So basically it goes to my DNS in my network, and then the DNS takes it to the root zone that knows where these GTLDs are and CCTLDs are. And then it bounces that to .lb, because it tells it, I don't know exactly where that address is, but I know where .lb is, so it goes to .lb. Then after that, .lb says, I don't know where where the exact address is, but I know where .edu is. And then so on and so forth, until you get the reply of the IP address of the service that you're actually looking for, and then you establish your connection with it right away. Now, all of this happens at a drop of the hat. I mean, from the time you type in www.aub.edu.lb and hit enter until the page actually loads, this is what happens in the background here. Now, the reason why I'm walking through this is because this system was always based on trust, right? You never looked at the Google or the university website and went, does this look fake? I think it is. I don't know. The logo looks off. The route, the spelling is off. I don't really trust this, you know, because you expect when you type in the URL that you would get the website that you're looking for. However, if somebody malicious was trying now to take you to a place, for example, if you're doing online banking and you're going to put your credentials on there, and somebody malicious wants to get your online banking credentials, he can actually inject throughout the path a bogus and fake IP address of the bank, directing you to his stuff. And then he would actually get and put up a page that looks like your bank, asking you for your credentials, and then he now has your information. Now, this system was based on trust because at the time when it was designed, they were saying, well, why would somebody do something like this? Because again, it was still a small experiment. Not everybody was on it. Now that we have half of the planet on there, you have people that want to rig the US elections or make people, you know, give up their banking credentials and so on and so forth. And that is why they came up with, at the IETF, with something called DNSSEC to secure the DNS system. And what it does is it certifies the whole chain, because the chain is only as strong as its weakest link. So if any bit of that chain is compromised, then you can still eject and do the bit that you want to do there. And that is why it has to be completely done on all that level. Now, on the root name server level, that is done. Sadly, moving down, especially in Lebanon's case, for example, looking at .lb, .lb has some bits signed, but afterwards, you don't find this, the DNSSEC implemented. And that's something that needs to be worked on here in Lebanon. Now, other countries are doing a little bit better with that. Some of them are doing a lot better with that, but that's something that also will be more and more of an issue, especially now also with IoT, with other bits, and you want to trust the answer that you get, because till now, you've never suspected that when you type in a URL, that the website that is loading isn't really the one that you actually intended it to do. You trust the device, and the device still trusts another device. And that's how hackers get away with the stuff that they get away with. Now, for these root name servers, there are 13 of them, 13 different ones deployed all over the world, as you can see here. Now, in Lebanon, there are 4 of them at this point. So that's good, because that means you don't have to go out of the country to resolve a new domain name. There's K-root, L-root, E-root, and another one. I don't remember what it is now, but yeah, it's so 4 different root servers that are here in Lebanon. Now, the organization that overlooks this is an organization called ICANN. That's the organization that deals with all the bits that we talked about. Who's disputing over who has the right to use which generic TLDs? How will you properly register people for their domains? Because you also want to make sure, especially for, let's say, law enforcement agencies or for looking up who's doing what, you have to make sure that the information, for example, in the WHOIS database, when you look them up, is accurate and up to date, because you may want at one point to actually bring down the website if it's doing, let's say, something illegal like trafficking narcotics or something like that. And all these things are being discussed, whether from the technology side and the policy side, and again, in open forums, at the ICANN meeting. There are 3 of them every year, and they discuss all this stuff. They talk about DNSSEC, they talk about the technology, how registries should work, how domain names work, and the political bits that go into them, policy bits that go in there. Now, the point that I'm trying to make throughout identifying some of these organizations is they are all open for us, that you can participate on their mailing lists, attend their meetings, actually change and shape how the internet works. And that is how the internet has been successful, that it's been always open, and using these open standards and using new ideas from people all over the world, people like yourselves, that can actually change how technology works and how the internet actually operates, even on its core fundamental basis and levels. Looking at the internet again, we said that we have 55,000 autonomous system networks, right? Now, these constitute the ISPs of the world, the exchange points of the world, the enterprises of the world, everybody that has a network. We said what an ASN is, and we've defined it, your identity online. Each one of them, interconnecting together, has a new piece to add to that. Because I could be a content provider that has the content. I could be Google, I could be Akamai, I could be, the university network here that has the website. But I don't necessarily have the customers, I don't have the users. When you're back home, you're on an IDM network, or you're on an Ojero network or something else, or a touch network, right? So through that interconnection, usually one of the operators would provide the contents, right, that is relevant to people. The other one would provide what they call the eyeballs, the users, people like yourselves that want to view and use that content. And through that collaboration and cooperation, they both benefit. Now, to get connected to the internet, like we said now, a network, let's say like the university campus network here now, it needs to be connected to a connected network to the internet, an upstream as we call it, right? And they usually pay to get their bits back and forth from that from that network, right? Now, it's best if you have more than one upstream provider. That way you can guarantee redundancy. We've heard that the AUB here, you do have redundancy. That way, if one of the networks goes down, the university network doesn't go down, and you still are able to reach the rest of the world. However, in some cases, some of these upstream providers are out of the country, which means that you end up sending everything that you send out, you pay for it to leave the country. Now, that's fine if you're doing international connections, right? If you're requesting information that lives out of the country, that makes perfect sense, right? But if you are, for example, in the university network here, right, and they have an upstream, and you're at home, you have another upstream, and they don't communicate directly to each other, for you to view local content in your country here, you end up leaving the country, paying for that communication to happen back and forth into Europe. You probably have added the delay that we talked about because of physics, and that's all the money that you send out of the country, right? And it has security risks that I'm going to address in a second. Now, the solution to do so is to build a local exchange in the country here, where these operators can actually come together and meet at one neutral facility, and that way they exchange the traffic locally here. That way, physics is happy because you're not getting the delay. People are reducing the money and overhead and cost that they're sending out of the country, and they're actually investing it into building infrastructure in the country. The third bit is the security bit, which is that after Snowden revelations, you all know Snowden, right? And you know the stuff that happened after that. There's a movie of it, actually, out there now. And what happened afterwards is that a lot of countries actually came up and said, we are doing deep packet inspection for all the packets that come into our country. We want to look at the traffic that's happening in our country. Not only just our citizen, any internet traffic that's coming into our country. Now, we said that these autonomous system networks have to interconnect, right? There has to be these exchange points, whether in the country or outside of the country. And there are some of the major ones throughout the world, some of them in Germany, some of them in Amsterdam, some of them in the UK, some of them in the US. So there has to be at least a point where these networks come together and meet. Now, if you elect to send your traffic out of the country, to get exchanged in one of those countries that openly say we do deep packet inspection, then you are actually putting yourself at risk to be, scrutinized, and people looking at your stuff, whether it's personal, whether it's sensitive to government or to yourself or to your work. That actually is a problem that actually happens. The German exchange point, DICX, which is one of the larger exchange points in the world, actually sued the German government because the German government wanted to do deep packet inspection on the traffic that they have. And DICX at the time, they said, well, you have the right to look at the German traffic. We can't really say anything about that. But there's traffic from everywhere else in the world coming into our network here. And the German government came back to them and said, well, if they choose and elect to send their traffic into my country, it is my right to do in my country what I see best. And thus the exchange lost the point, the trial. Here in Lebanon, there is an exchange. Actually, there are a couple more exchanges that are being popped up. There is a discussion that's going to happen today and tomorrow about the exchange and the future of the exchange. If you're interested, see me for details. Shafiq knows where the place will be exactly. My colleague, I don't know where it is, but I know it starts at 2. But there are discussions about this, and this is something that also touches on, everybody using the internet, whether they know this directly or not, but it is an important discussion of things moving forward. I won't take more of your time. There are a couple of recommendations I have here, but if there are any questions, let me know. If not, thank you very much for coming and listening, and it was a pleasure. Yeah, please.
Is there any IP recycling?
Yeah. So what would be considered to be IP recycling is, and I'm talking on a global level, not just on a network level, is, for example, so the 5 organizations that I mentioned, right? They distribute these resources to organizations. Now there is the possibility that these organizations run out of business, for example. They bankrupt, they do mergers and acquisitions and buy each other out. They run a project for a while and then they say they don't need those resources back anymore. So what is requested from them is once they do that, they give those resources back. Because technically when we assign or allocate those resources to a member, we're not giving them ownership of those resources. What we're giving them is the right to use those resources for a year, as long as he's a member and he keeps on renewing. But like I said, if they go bankrupt, if the project ends, or they have no use for those resources, they are expected to give those resources back to the RIR, the Regional Internet Registry, and they get recycled again. Now, a lot of people do this. A lot of people see an opportunity to make some money out of this, because when supply is a lot less than the demands, then you create parallel markets, right? And some people see an opportunity to make money out of this, where, for example, I would say I have a little bit more IPv4 addresses than I can use, and I know you need them. I can actually sell you the right to use those resources and what we've seen the market numbers go for is around roughly $10 per IP address. It goes up if I'm giving you like a bigger block, but roughly it's around $10 per IP, right? So basically we do that deal, and then what happens is we go back to whatever RIR, in this case RIPE NCC, and we ask them to update the records. Now the NCC doesn't have anything to do with that transaction, but it does want to make sure that these records are up to date for a lot of different reasons. I mean, these IP addresses are used for geolocationing, for example. When I came here to Lebanon, it said, "Welcome to Lebanon" on my Facebook account, right? It identified me through my IP that I wasn't in Dubai anymore, that I've actually moved to Lebanon when I came here. When you type into Google and say Chinese restaurants, you don't get Chinese restaurants in China. You actually get them here in Lebanon, right? Because it's identifying you through your IP. Now, if a transfer has been made out of China into Lebanon here, and those records haven't been updated, right? Whenever you type in Chinese restaurant, or even like if you say Lebanese restaurant, it will give you Lebanese restaurants in China, right? Because geolocationing has broken now. That's one aspect of it. So that's why keeping those records up to date is very important. Yep. Any other questions? Yeah, please.
Okay, for the location of the IP, if the NAT was supposed to be started somewhere in Europe,
Yeah.
and it's nabbing all the way to somewhere in Lebanon,
Yeah.
my external IP was typing Google will be somewhere in Europe, not
Yeah. So that I actually had that. I was in Ethiopia at one point, right? And I went and I typed in Google, and I got Google Israel, because Ethiopia was getting their IP addresses natted out of Israel through the upstream. The public IP address I got was out of Israel. And that's the thing. That's exactly the case that you would see. Now, a lot of them don't really do it that way. I mean, again, this was Ethiopia in Africa a couple years ago, so it wasn't as developed. You will probably be natted by an operator in your country, so you don't necessarily face that risk that often, but it could happen. Yes.
But you said Africa basically didn't run out of IPs yet.
No, they haven't. But again, this goes back to how, in this particular case that I gave you, is how they developed their network. That basically the Ethiopian operator just bought transit out of Israel directly because they had a cable, and they were using their IP addresses and not doing what they were supposed to do of building their own, getting their own resources and doing it the way properly. Again, this was a couple years ago. This was at least 7-8 years ago. I'm guessing now that the case has become better, but you do see stuff like that. You do see this more and more, I think in Europe, for example, because now Europe has kind of taken away borders. They're thinking of bringing them back again, but for a long time they took that out, right? So it was easy for you to be in Belgium, for example, but your ISP is actually in the Netherlands. So when you would look up your IP address, it would say you're in the Netherlands simply because they have a direct connection into Belgium or their neighboring country. So you would see that sometimes in Europe, but it's not as bad as it would seem. But yeah, it could happen. I've seen this particularly in hotel networks, where the branch just, because they have different branches all over Europe, so they just buy from one major ISP and they divide their network throughout their network. So you can be in a country, but it sees you as in another country. But again, these cases are very rare. You wouldn't get this on if you're a customer, if you're a resident in the country and you used DSL or use something else, you wouldn't probably get something like this. Unless you want this by design. There are other ways that you do this by design for other reasons, like when you VPN into another country, for example. You can get something like this, yes. So for example, in Iran, because a lot of content is blocked there, so they get VPNs into the US so that they can actually view content without the restrictions that they have from the government there, right? Yeah, please.
This is how it works currently today with all the IP distribution and stuff. Lately we've been hearing of the new internet providers type, like the giant airplane that Facebook is building.
The drones.
Yeah.
Mm-hmm.
The satellite provided to cover Africa, or the hot air balloons.
Mm-hmm.
How does this fit with the whole spaghetti?
It's a good question. The thing about this is these are the ways that they deliver This is the access infrastructure bit, right? I mean, technically, as far as the internet is concerned, whether you get connected via fiber, wireless, a drone, a hot air balloon, it doesn't make a difference if you get connected to that. Now, that will probably add to the question that was asked earlier. For example, if Facebook is sending out a drone over Africa or somewhere to give resources, it will probably be seen as Facebook US addresses, for example. But in general, they would still connect the way that you connect to Wi-Fi or you connect to any other way of interconnection.
What is the relationship here between the regulations set by the countries versus the internet?
Yeah.
You mentioned something about VPN, but currently is this considered legal? Is this considered by the Internet Society? This is open freedom to access the data.
Yeah. So that's also a very interesting question. There's a lot of debate about that, right? As far as, look, if I'm giving you my techie answer as a techie, purely as a techie, technology is technology and should be used, right? However, putting on my actual work hat, because I do work with a lot of regulators, there are certain things that the government takes into consideration for good reasons and for bad reasons, right? I mean, sometimes they legislate against technology to prevent it for, let's say, financial reasons or something like that. We've seen a lot of it with voice over IP in a lot of countries, for example, where they're saying, we don't want the incumbent to lose money out of voice over IP, so it should be illegal in the country, even though it's a technology that even the incumbent is using, but they're preventing you from using it just to save those margins of money. So that's not necessarily a good reason, but there's sometimes good reasons to legislate against using certain things at certain times and introducing it when the people are ready. I know for a fact that regulators do not like legislating against technology per se, either for or against. I mean, they could be all pro IPv6, but they don't want to say every operator has to move to IPv6. They could be all against NAT, but they don't want to say you cannot use NAT on the network. It's bad regulation to regulate against technology per se. But yeah, every country has its unique circumstances. And in general, it is accepted that a country has the sovereign right, like we said about Germany, for example, it has a sovereign right to do in its country what it sees best for its citizens. Because it goes back into culture, it goes back into the way people interact, it goes back to even political and financial considerations in the country. I would mention, for example, at one time, maybe you guys would remember this, there was put on YouTube a movie that was considered to be offensive to Muslims a couple of years ago, and a lot of people went out and protested against it, right? And at the time, I mean, even governments like the Egyptian government, for example, I think the court ruled against against YouTube and said they should take it down. Now, as far as Google and YouTube were concerned, the Egyptian government had no say over what they were doing, but they actually eventually took it down when somebody lost their life. I think in Libya, somebody was killed during the protests, and that's where they get, okay, freedom of speech is one thing, losing lives is another. So it's an interesting debate that is always done. There's something called the Internet Governance Forum, where a lot of these issues are brought forward, where basically what is said is all these guys need to work together and coexist with a framework, especially also with government, with regulation, with other bits as well. And at that IGF, they meet with the different stakeholders and discuss with them these topics and try to find middle ground of letting go of certain things. And we've seen this. We've seen countries that had monopoly operators opening up their market and liberalizing it. We've seen countries that were regulating against voice over IP that opened it up in their markets based on these discussions and understanding that you cannot keep technology from moving forward, because at one point you will need to use it in one way or another, and you just cannot stop doing this. I remember a time, this was a long time ago, where Wi-Fi in my country was actually considered to be illegal. Because the military owned the airwaves, right? And then and the Ministry of Communication had to battle for a long time to get those airways done, and they could only get the 2.4. 5 is still considered to be illegal because they say that the radars uses the 5 gigs, and then it would be using, crosstalk and miscommunications and stuff like that if they do that. There are certain things out there. Like I said, there are sometimes good reasons, there are sometimes bad reasons. But through these dialogues, things get moving forward. Other questions? Yeah, please.
Most devices now send encrypted traffic.
Yeah.
How does that affect the packet inspection?
In fact, how does that affect? Packet inspection. It makes it a little bit more difficult. It doesn't necessarily make it impossible, right? Because basically, I like giving examples of movies because I like watching a lot of movies. There's a movie called, yes, thank you. Yeah, which basically talks about how they were breaking the encryption during World War II. And what came out of that is these devices. Funny story about this. The Apple logo on this device is because the guy that did this, Alan something, yeah, Alan Turing, thank you, I blocked on his name. He actually committed suicide eating an apple. And that's why Apple has this logo here. Yeah, cool tidbit there. But so the idea is that when you use encryption, they say that a regular computer would take probably, I don't know, let's say, depending on how good the encryption is, but let's say it will take 600 hours to break your encryption with all the different permutations that I can actually get in order to figure it out, right? And that's what makes it really, really strong and good. But the thing is, over time, these things, there's something called Moore's Law, where basically it says every 2 years, the smartness of these devices doubles, because you can add twice as many transistors into a chip, right? So it becomes twice as smart every 2 years. So what would take me, let's say 600 hours 2 years ago, would take me probably 300 today, will take me probably 150 tomorrow, assuming that we're talking linear here, right? That's taking into consideration just normal laptops. That's not taking into consideration quantum computing. That's not taking into consideration supercomputers, right? So even though you would say, yes, it would take a regular computer to actually take this much amount of time to break this, if you have access to like a supercomputer, that 600 hours becomes 6 minutes. And then, but encryption is still, don't get me wrong, I'm not encryption. I actually am very pro encryption, whether in your email and other stuff, because it does create that barrier. However, does it make you completely impenetrable? No, it doesn't. There is ways around this. I mean, we've all heard about the case where the US government wanted Apple to put backdoors on their devices. Remember for the FBI case, if you've heard this? Have you heard the story? Yeah. So what happened was, the Apple was pushing back and they didn't want to do that, right? And then all of a sudden somebody came out and said, okay, no, for the sake of this, I will break Apple's encryption, even though Apple keeps on saying it is secure and nobody can break it, nobody can do that. Because there was this unique situation where they had to do that and they had to compromise every single device versus that one device. Somebody went out and said, okay, I'll do it, and he actually did. And that's the thing. I mean, encryption is great. It will keep out, let's say, 99% of the people that are trying to do malicious stuff to you. But does that mean that nobody can ever do anything to you? No, then.
So does that deep packet inspection include decrypting your packets and
It depends on the system that they're using. Again, like I said, if they're using a more sophisticated system, it probably can. It depends on the system. But again, doing encryption is making their jobs a lot harder, right? And again, it's just a matter of, because I get that question a lot, is can, you know, and not necessarily in Lebanon, but I get this in other countries as well, can the government actually look at what I'm doing in terms of traffic, and can they figure out what I'm doing, even if I use encryption, even if I use something like Tor, even if I use other bits? If they really want to, yes, they can. However, you also need to look at it as a cost versus effectiveness model, right? I mean, how much would they actually spend to monitor every single piece of device and every single packet out there, especially if they're using encryption, especially if you're making their lives a lot difficult to actually do so? The answer is, if it costs them a pretty amount of money, then they probably won't do this. They would look into you specifically and zoom in really, really much if they have like a good reason to do so. But in general, just looking at everybody's traffic all the time, especially if they take into consideration good practices like using encryption, it doesn't make sense. It doesn't scale, let's say.
how do they know what to zoom at if they're getting
No, I mean, if, for example, if they suspect you for any particular reason, like the guy that they found the phone for the FBI case, basically what they were asking for is they wanted his contacts, right? They wanted to see who he actually calls and, well, they can get his call records from his mobile carrier, right? But they wanted to see the information on the phone. Because if he has a picture with 3 other people, then maybe we need to look into these 3 other people a little bit closely and make sure that these are, you know, people that are in good standing. Maybe they are part of his cell, maybe they're not, right? So, and in that case, then yeah, it becomes a little bit more, or a lot more aggressive. But in general, it doesn't scale. Let's put it that way. Unless that government is really, really, really paranoid, it doesn't scale. And it has a lot of money to throw away because it will take a lot of money to do so. Like for example, in UAE, they have a law out there that criminalizes using encrypted VPN, for example, right? However, we discussed this with the regulator and said, because I use encrypted VPN to dial back to my home office in Amsterdam to check my email on a daily basis. That means I'm breaking the law every single day. When we chatted with them, they said, well, it's not necessarily to prosecute you or put you in discomfort, but what it is in case people are using this for the wrong reasons. For example, if we suspect that somebody is doing, let's say, narcotic trafficking over something like this, then they can get him on breaking that law. You get the point? Yeah. Yeah, please. No, not for IPv4 over IPv6 and not for IPv6 over IPv4. The thing is, at the end of the day, they are addressing schemes. They are a way for you to find your way. If I would say now, if you lived at 16 Khoury Street, for example, right, and I changed its name to a more complicated name into you now live in 16 Khoury 1, 2, 3, 4, 5, 6, 7, 8 streets, right? It's still your address, it's still the way that I find you with. Now, security is an important thing, especially with IoT and other bits coming in, and people like securing every single bit of it. The addressing bit, and there are bits to do this. There's something called IPsec that secures IP addresses. There's something called RPKI that certifies that you're the rightful owner to use these addresses. However, at the end of the day, addressing is just the addressing bit. It's just the plumbing there. And a lot of people that are talking about security are talking more about it at the application layer to make sure and authenticate that you are the person with the rightful access to actually use this, not just the addressing bits, right? But again, the only reason why people prefer IPv4 to IPv6 nowadays is it's familiar. It's the first thing you learn when you take the any networking course or any job description when you join. It's the first thing you learn is the IPv4 and how to do NAT and how to subnet and how to do the other bits. So it requires a little bit of paradigm shift when you look at IPv6. Yesterday we were at the Bellarmine University, right? And I sat with the computer science guys for 2 hours. In 2 hours, they managed to learn what we teach in a day's time for veteran network and ISP guys, because for them, it's kind of a green field, right? When you explain to them the thing for the first time, it makes sense and it clicks and it's there. For the experienced IT person or ISP person that we've been dealing with, that has been dealing with IPv4 and NAT for the past 10, 20 years, it still requires him to make that paradigm shift in his mind, and that's what takes us a whole day, because he's familiar with that, right? And that's I think where that resistance to move to IPv6 is still at. It requires you to think a little bit differently, because with IPv4 we count the number of users, the number of devices, and we try to conserve as much as we can, because we started building our networks after IPv4, we predicted it to run out. Whereas with IPv6, for a point-to-point connection, I would say when you're doing your IPv6 planning, plan for thousands of IP addresses. Only use 2, but plan for thousands of IP addresses, because it will just make your life easier, and we have enough to go around, right? And that paradigm shift is, I think, what's keeping people from actually moving forward and deploying IPv6. Yeah? Other questions? Okay, well, at that point, thank you very much for coming, and thank you for your questions. I really enjoyed this, and I hope you did enjoy this as well. Thank you. Thank you.